In this video, we are going to talk about the temperature and reaction rate. Uh, I have dealt with the effect of concentration of the reactants and products on the rate of reaction in much details, and all of this I have done considering a given temperature level. You can check on the playlist of this video for those lecture videos, but our complete understanding of the reaction rate or reaction rate equation is also dependent on understanding the role of temperature. Okay, if you observe a typical rate equation for a reaction, say A gives products, then the rate equation will be like minus Ra equals to minus 1 by V dNA dt. Now, Na here is the number of moles of A, dNA being the change in number of moles of A with respect to dt, the time change, and V is the working volume. Now, if you write this, you will write this using two terms, K into F of C. Now, this F of C is basically the concentration dependent term of the rate equation, and this K over here, this is known as the rate constant or temperature dependent term. Okay, so the concentration dependent term, this remains usually remains unchanged at different temperatures, but this K or rate constant is extremely dependent on the temperature of the system. Now, as per the chemical theory, rate constant should be temperature dependent by following this relation. K varies as T to the power m e to the power minus E by RT. This is what chemical theory says. Okay. Now, through different experimental studies, it is seen that this exponential term is very important because this term is more temperature sensitive. I am writing this for the sake of easier understanding. This is more temperature sensitive than this power term. Okay, so for ease of studies, people generally consider this relation to be more effective. Okay, because of higher temperature sensitivity. So, after finding the concentration dependency of the reaction rate, the next target will be to find the temperature dependency, okay, or how the rate constant varies with temperature. And to quantify that, we use the Arrhenius type relationship. So, Arrhenius type relationship. This is what we use. Now, what does this say? This simply says that K equals to K naught e to the power minus E by RT. This K naught, I think I have spoken about this in some other lecture also. This is actually a pre-exponential term. Okay, so this is a pre-exponential term, and this E over here is the activation energy, and the unit is joule per mole. Generally for studies we adopt this unit. Okay, it may also be kilojoule per kilomole, which gives the same measure, or kilojoule per mole, but as per your study you have to convert the units. Now, if you want to you know determine these terms, what you will simply do is you will plot a graph On your x axis you will plot 1 by t, and on your y axis you can plot ln of k. So you may get a straight line, and you will obtain the slope as minus e by r. So this straight line is the best fit from the experimental data. Okay, so that will give you your understanding. If it is, if you have the information that you know the rate constant at two different temperatures, then you can use the relation ln of k2 by k1 equals to e by r 1 by t1 minus 1 by t2. Okay, so this is the general relation. Now a shift in this activation energy with temperature definitely reflects that there is a change in the controlling mechanism of the reaction, and this can be accompanied by some change in the concentration dependency as well. So for very complex systems, these kind of change in the controlling mechanism of reaction is also studied with a I mean, considering a much greater possibility of these phenomena happening. But for simplistic studies, we generally stick to the basic understanding about how rate equation depends on the temperature dependent term. This more or less outlines our basic understanding of temperature dependency on reaction rate. See you in the next lecture. Thank you.